So good afternoon to everybody, and many thanks for inviting me today at this meeting. So the topic of my talk, at the center of my talk, are two-dimensional material, meaning material where the motion charge carrier is confined in a layer plane. And these are semiconductors, means that you can use ultra-thin material to make interesting quantum system functional devices. But there are a number of opportunities, but also challenges. Don't know yet how to align high quality. I'll show in this talk my research that is about exploring opportunity, but also trying to address challenges in the making of this system. So before starting with my talk, I'd like to tell you a little bit about my university. We're in Nottingham, from the very heart of England, the red spot. So we have 3 campuses. This is one of the largest campuses in the UK with over 40,000 students. 2 campuses are outside the UK, in Malaysia and China. And normally Nottingham is associated to Robin Hood and the Nottingham Castle, okay, and the Nottingham Forest, which is not very far away from Nottingham. But perhaps not many knows that Nottingham is also famous for very important physicist, George Green, who is the mathematical physicist who proposed the first time the idea of potential in electrostatic, and also they introduced the concept of green function that these days is used across different disciplines. And it is this work from 1828 that introduced this mathematical formalism, the green function that is used still these days. So 1828, 200 years, almost 200 years ago. And what is astonishing that he was writing this important work, these important essays, while working in a mill, in a windmill, as he was making bread. And during the spare time, he had this brilliant idea of, for example, the idea of potential, non-locality, that's so important in electromagnetism. Now, this is still used these days, and it was also used by our colleague in Nottingham, Sir Peter Mansfield, for the development of MRI, magnetic resonance imaging, that then led to the 2003 Nobel Prize in medicine. And there are many other examples of important applications. So if you come to Nottingham, please visit the windmill, which is still operating as a mill, but is also a science museum. And of course, visit the University of Nottingham. So let's go back to the main theme of this talk, which is about semiconductors that have been around for a long time. They are referred often as the brain of modern technology, special material with electronic property well suited for a wide range of application. But sometimes we forget that all this extraordinary technology built up on important discovery in condensed matter physics. And in the next slide, there is just some example of Nobel Prize discovery in semiconductor physics, starting from the discovery of the transistor that actually was based on understanding of the band theory, which was mentioned this morning. And then there are many involving two-dimensional system, for example, the quantum effect, using a multi-layer structure and traditional semiconductor, but more recently, in 2010, the discovery of two-dimensional graphene has completely changed semiconductor physics, semiconductor technology. Let's see the importance of this discovery. So the first important fact that they realize is the possibility to use a bulk crystal, in this case graphite, to delaminate. Yes, okay, sorry. Okay, so they realize the importance of using a van der Waals crystal like graphite that consists of several layers of carbon atom weakly coupled. So to use this van der Waals crystal to isolate a single layer of carbon. And they were doing that using a very rudimental Scotch tape technique, pressing Scotch tape on a bulk crystal, then removing few layers and transferring them on different substrates. But they didn't get the Nobel Prize just for using this rudimental approach, because graphene was actually well known theoretically. They made a device, a quantum Hall effect device, demonstrating the possibility to create truly two-dimensional electron gas and the possibility to observe 2D conductivity, two-dimensional conductivity. Now, this, as I mentioned, has had a big impact in semiconductor physics and technology. You all know about the Moore law and this trend of miniaturizing semiconductor, traditional semiconductor like silicon. But as you make silicon smaller and smaller and smaller, you reach a bottleneck, because as you make silicon smaller and smaller, the electronic property of the silicon deteriorates and become more and more difficult to use such small silicon or to integrate in an integrated circuit. And but silicon is still a favorite semiconductor electronics because of this possibility of creating this large wafer and convert in integrated circuit. So, but can we do the same with graphene? Perhaps not with graphene, but following graphene, there has been an explosion of interest in a number of other van der Waals crystals that can be delaminated, can be converted into atomically thin layers. And this is not only important to make semiconductors smaller, but it's also important to explore a number of interesting quantum effects that are difficult sometimes to observe with traditional semiconductors because, for example, constraint in combining different material or obtaining high-quality quantum confined system. And there are a number of interesting new concepts emerging from the possibility of creating new charge and spin order in strongly confined system or entangled charge using two-dimensional platform or switching device based on charge tunneling, like the tunnel field effect transistor. So there is a large variety of two-dimensional crystals. And at Nottingham, about 10 years ago, working with a couple of PhD students, we isolated, using this Scotch tape technique, a new two-dimensional semiconductor based on group 3,6 elements in themselves. And you can see the crystal structure of this van der Waals crystal. And here you see a comparison of graphene and the single layer. So you see they both have hexagonal symmetry. One has a larger lattice constant than the other. And what we discovered that is truly a semiconductor because he has a band gap, strongly affected by quantum confinement. Is compatible with graphene, in the sense we can combine different layers, and we can make a quite interesting new structure based on the fact that it has extremely high quality crystal property, like a little bit of graphene, and also resilient to deterioration in air. So, for example, we work with André Geim, the Nobel Prize winner who discovered graphene, to realize a structure that combines graphene and this two-dimensional semiconductor to make extremely thin field effect transistor. We discovered we could get electromobility larger than any other 2D silicon or graphene transistor that has issue because graphene doesn't have a proper gap, so you cannot switch on and off the current. And so this led André Geim to comment that we have found a semiconductor that is the middle in between graphene, the golden middle between graphene and silicon. And an important indication of the quantum nature of the electron transport is the quantum Hall effect, the quantization in the electrical conductivity that we could clearly see in this multi-layer structure where the electrical channel is the 2D inside. So, and of course, once you have a nice two-dimensional electron gas, you can further confine the electron motion to create, for example, a quantum dot or a quantum wire to additionally confine the transport. So what we can do next? So in his famous lecture, Richard Feynman in 1959 mentioned what can we do with layer structure with just the right layer. And basically we can do everything. We can play Lego at the nanoscale. These are van der Waals crystals, so we can combine them together without the constraint that apply to traditional semiconductor. And so this is what we have been doing, combining, for example, this special indium silent semiconductor system with different van der Waals crystal, and demonstrated a number of interesting new concepts for processing information or for photonics. And so these are some of the device concepts that we demonstrate on spin bulbs that combine magnetic and non-magnetic semiconductor to MEM RISC that use ferroelectric layer. And all these device concepts are very important, for example, for a new way of computing. This morning we heard about neuromorphic computing, quantum computing. We need the hardware in order to develop this new technology. So, but how we do how most of people do this type of new structure? The approach is very rudimental, which, as I say, you scotch tape, press on a bulk crystal, and then transfer on a different layer. And you can see here the various steps. And this is not a scalable approach. I just want to give you an example how long it takes just to transfer single layer graphene on a particular substrate. And here I have a video. This was made by a research assistant in the lab, very frustrated by the time that it takes to make just to transfer single layer. And so he decided to show to others how this
In
is
this
done.
clip, we're looking at a needle transfer technique that we use in our lab to precisely control the deposition of 2D materials such as CVD grain graphene. We use a homemade setup consisting of an optical microscope and a stage controlled by piezoelectric motors. This allows us to move the sample with a precision of a fraction of a micron. Here's a close-up of the stage where we can mount our sample.
So
And here, in the centre of this copper coil, are the CVD graphene strips that we'll be using to transfer onto our substrate. Through the microscope, we see this dotted pattern, and each one of these dots, in theory, is where there should be a graphene strip. You can see the individual strips here in this close-up, and each strip is about 10 microns wide and 40 microns long. The graphene is covered by PMMA, which makes it easily visible under the microscope. So for this technique, we use a glass needle that has been formed with a very fine tip, which is about 10 microns, similar to our graphene strips. The first step is to bring the needle close to the graphene strips, and we can do this by changing the focus of the microscope between the needle and the graphene, and then adjusting the micro manipulators on the stamping arm to bring the needle down. As well as adjusting the height, the micro manipulators can be used to move the needle in the plane, so we can align the tip above a specific graphene strip. Once the strip has been selected, we bring the needle into contact, and we know this has happened because we can see a slight distortion in the surface. We then have to apply some pressure to the graphene to dislodge it from the surface. This can take a few attempts of jiggling the needle around to get the PMMA on the top of the graphene to stick to the needle and completely dislodge it. Now that we have the graphene on the end of the needle, we can move it around to our desired location. So now we need to bring our substrate into the view of the microscope. Here we're using a sapphire substrate with generously sized gold contacts. Similar to picking up the graphene strip, we bring the needle close to the surface of the substrate. We have the capability to independently move both the needle and the substrate in all three directions, as well as rotation and angle. This gives us the power to deposit the graphene, and of course any other 2D material, on a substrate of our choosing with extreme precision. Which means we can use a similar technique to build vertical structures of 2D materials, just like a slightly more complex version of Lego. Once we bring the graphene into contact with the surface, it sticks to it via van der Waals interactions, which are stronger than the sticking force of the needle, so that when we retract the tip, the graphene is left on the surface of the substrate. We then bake the sample at 180 degrees Celsius for about 10 minutes to improve adhesion, and then perform solvent cleaning and anneal at 300 degrees Celsius to remove any PMMA and impurities on the graphene surface.
Okay, so this is just to show you how difficult it is dealing with this atomically thin layer. And this is just one of the multi steps in the fabrication of a device. So, and this is why a few years ago, in about 2018, we realized that we had a way we worked in this make two-dimensional material in a different way, using a bottom-up approach rather than using bulk crystal and reducing that to the layer. So we came up with this idea of a new facility that we call AP2SEM, that stands for epitaxial growth and in situ study of two-dimensional systems. So you can see is a 3-chamber cluster in ultra vacuum. So it's quite complex system. What we have a first chamber. When I say UHV, ultra vacuum, means 10 to the minus 10 million. So we really need to have an high purity environment to grow or to develop this system. And also with the atomic resolution. This is how it works. Element sublimated from the solid source and then crystallized on a substrate that kept at a given temperature. So this is done by a technique called molecular beam epitaxy. Then in ultra vacuum, we take the sample to the second chamber where we look at the morphology using technique like scanning tunneling microscopy or atomic force microscopy. And then the third chamber, actually quite complex instrument, to use the photoelectric effect, let's say electron spectroscopy, to measure the composition and the electronic structure of the material. So the idea of, so all the 3 chambers are connected in ultra vacuum. So we can operate them independently, but we can move also the sample from one chamber to the other in UHV. And so this is the idea of cooking and tasting. So different way of developing material using a system where you can try your recipe, you can see what you have grown by looking at both the structural property and electronic property. For example, using angle resolved photoemission electron spectroscopy to measure the bands of the system. And we have entry and exit point which means that if our material are good enough, then we can take our sample to other facilities, for example, to use them to make devices. So to establish this facility, we have to create a new lab, quite large lab, converting a workshop and a toilet into a large lab with this very long, we call linear transfer line that connect in UHV the different chambers. So we received the various components of this bespoke system in 2021. Here you can see the picture of all these huge boxes that we received and we fill completely the lab space. And this is how the lab looks like today. We completed the installation in 2022. So you can see the long linear transfer line and the three chamber. This is about 10 meters in length, and this linear transfer line is critical to reduce mechanical noise, so important to conduct measurements without of atomic scale system. I want to give you an example of things that we have been doing since they installed the system. We focus on creating this new building block for electronic component based on this semiconductor, gallium arsenide. It's a van der Waals layer, single van der Waals layer, sitting on top of graphene. And there is this van der Waals gap because the two layers do not interact. So we grow this system in UHV, then without breaking the battery, we move to the electron spectroscopy study, so we can visualize the energy dispersion of the electrons. We can see the band structure, and we can discover this very unusual dispersion. This is called an inverted Mexican hat type of dispersion with extremely flat dispersion corresponding to large electron mass. And Van 't Hoff singularity in the density of states, they are so important, for example, to then explore electron correlation effect. And we can look at the symmetry. We can understand how the two layers align relatively to each other by looking at the energy surfaces and explore how this band structure change as we go from single to or multiple layer. So we really have control now of this nanoscale system with atomic solution. What is interesting is that we can then start engineering the electric field at the nanoscale. For example, as you bring one layer next to each other, there is a charge redistribution of the interface. Okay, so for example, one layer becomes more negative than the other. And so this corresponds to an electric field that can be quite significant, time just few hundred MeV over a length scale of few angstrom. And so we can use this built-in electric field to realize photosensor, where this built-in electric field is used to separate, for example, photocharges, electron and hole generated by light. Okay. And I think, so what's next? We are looking and developing different systems. And as I say, this is our first restaurant in Nottingham, where we cook and taste two-dimensional material system. We want to link to other facilities in the UK and abroad. This is possible because we can use UHV suitcases to bring around materials, still maintaining this very clean environment. And the facility now is open for collaboration with anyone who is interested in developing this space. And so let me conclude with two things. First, acknowledging the contribution of so many students and staff, both in in Nottingham, but also the funding body and collaboration. And we have provided material to many institutions in the UK, abroad, and we're still willing to create new partnerships. So because I have time, I perhaps can show you the video of when the facility was delivered and then installed to show you the scale of the challenge. And I will stop here.
Thank you very much. Very nice talk. I wonder, wouldn't you ideally have this facility inside a clean room where you can also do the fabrication and device work?
It's 4 or 5 million more, yes.
Well, I 50 million. I think our funders are not ambitious enough.
Okay, so of course, there is no limit in the complexity and how large can be the facility, but you also want to make it practical to access. And so what is important is that inside the system is clean. So we don't need in a clean room to operate.
Sure, of course.
And of course, using suitcase, we can transfer material from UHP to another UHP facility. So, but of course, ideally, you want to have a big lab, you have everything, but then it becomes, as I say, less practical because already with this system, there is lots of coordination going on. And we meet regularly every Friday morning, 9 o'clock, to review what we are doing, because it's like 3 different experiments. We need to ensure that UHP is maintained, and nobody do stupid things like entering a sample that may contaminate, for example, the so yeah, it's quite a difficult system to work, but we don't need a clean room.
Yes, people, thank you for a great presentation. So the first question is, all research on quantum gates has been conducted at low temperatures, brackets 152 millikelvin. So what about at high temperatures? Are there any challenges or potential benefits? Ooh.
Yes, of course. Yes, there are examples of gated structure to introduce a quantum confinement in the layer plane. And the electronic properties to the layer are critical to see quantum confinement effect at low or high temperature. So you need extremely light electrons to be able to go to room temperature. And so this is part of developed materials that we are still doing. So this quantum confined, quantum gating effect, the center is still relatively low temperature. So there is definitely space for better.
Great, thank you. Sorry, excuse my voice and on the speaker in here. On a similar vein, what about quantum dots in high temperature?
Quantum dots, yes. So you can use a 2-dimensional platform to create a quantum dot by the study technique. However, you are limited about how small you can make the quantum dot, because using metallic gates, for example, electron lithography, electron beam lithography, we can make things small, but also the material properties are critical to have strong quantum confinement effect, even if you have relatively large dots. So yeah, it would be nice once we have the perfect system go into this area.
Thank you very much.